What'd you say?
I hate Blackboard.
What?
Because, like, when it logs you out, it doesn't give, like, any option to log back
Oh, it
in.
doesn't give you like the button.
Right, you have to completely reload
I see.
the tab.
Okay, so last time we wrote adding stuff to the binary tree kind of externally, right? And I mentioned that, so for our homework, we're supposed to do this using kind of an internal approach, asking nodes to add to their left or right, that kind of thing. That was the homework, right? Okay, okay. So let's just create another one of these. We'll create a public void add to. This guy will take in an int payload. All right, and we will handle the default case or the trivial case out here. So if this dot root is equal to null, then we'll say this dot root is equal to a new node created with that payload. And then we'll go ahead and do our system.out.println root right there for our directions. All right, so otherwise, we must be adding this somewhere in our tree. So what we're going to do is we're actually going to tell the root node to add this node to itself. So we're going to teach nodes how to add a payload. All right, so now an individual node will know how to add a payload. So they're going to ask the question. They're going to say, if payload is less than or equal to this dot payload. So from a node's perspective, if the payload that I've been asked to add should go to my left-hand side, if it's less than or equal to my current payload, then if this dot left child is equal to null, that means I have a space for this guy, right? So I'll go ahead and place him. So I'll say this dot left child is equal to a new node made out of that payload. If my left child isn't available, there's no vacancy, I'm going to ask my left child to add this node. This dot left child dot add payload. So if the guy should go to my left, if I don't already have a left child, so if I don't have a left child, go ahead and create a left child with this new payload, then I'm done. Otherwise, I'm going to go ahead and ask my left child to add this payload on my behalf. I'm passing the buck to him. All right, so that's what I do if the payload should go to my left. If the payload should go to my right, else, if this dot right child is equal to null, if I don't have a right child, then I'll set my right child equal to a new node built using this payload. If I do already have a right child, then I'll ask my right child to add this payload. That make sense?
So the left child and the right child are allowed to have two payloads?
No, they only have one payload. If I don't currently have a left child, so let's say I'm the root node and I have no children, and this payload that came in is supposed to go to my left. I'm going to look down and say, oh, I don't have a left child. So I'll go ahead and create a new node out of the payload that was just given to me, and I'll set that node as my left child. Otherwise, I'm going to ask, let's assume I did have a left child. I'm going to ask my left child to go ahead and add this payload. So now my left child will have this same version, this same function called. So this is kind of like pseudo recursion. So my left child, this guy down here, let's say I become him for a second. Okay, so now I'm the left child. I receive this payload I'm supposed to add. I ask myself, should this go to the left or to the right of me? If it should go to the left, do I currently have a left child? If no, I'll create one and put him there. If not, I'll ask my left child to add him. So I'm just passing the buck down and down and down until one of my children finally has a place, either left or right, to create a node for this guy. They're not replacing their own payload. They're just placing this node underneath them wherever it should go. Okay, so if we're going to add it to the left, we're going to go ahead and just do a system.out.print. And I'll print out left with a space like that, just so we get a pretty similar type of look that we had before. Similarly, I'll do that here for right. So this will either be the end of the road if that's it right there. Otherwise, this guy will likely print out something else. All right, so there's how a child can internally, or a node can internally add a payload somewhere along the tree. Go ahead.
Do we maybe want to add a print so that we know when a node has actually been set, so we can see left, right, set, left, right, set.
Well, the last thing will be the set. We will know that it's set with the very last direction. I mean, if you really want to say that, I mean, you effectively want to go in here and do a system.out.println set, and that'll be what kicks it down a line. That's fine.
Okay, but where's the new line going to come from otherwise?
I would have put it back out in the add at the other thing, out in our binary tree.
I see.
Yeah, so if you want to finally say that it was set, we could do that. So then in binary tree, all we'll do is say this.root.add payload. So that's what add to looks like if we internalize the add node into our nodes. Because we're just passing the buck into the node and asking him to find a home for this guy. Make sense? So let's test this. So we're going to be calling add to. For these guys. All right, and each of these should have a set at the end at the end of it. Actually, root won't have a set. Root is just going to say root. Oh, we have some errors in our code here because I took out or set left child and set right child. So let me just comment out add. Run this again. So there's our, I would have expected, oh, this is the disconnected. There we go. So here's our root, and then it's our right set, then right left set, then left set, then left left set, then left 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 set. All right, so this does the equivalent, but internalizes it inside of nodes. All right, so effectively, this is the solution to the homework. Just a couple of if statements. So this is kind of stretched out because we have some prints in there and stuff like that. So questions on how this works?
Is there a way we can write that in the binary tree class we use the while loop to get to the end of the node, the left child and the right child?
Well, we kind of did that last time. That's what all this was. So there's our while loop where last time we externally traversed the tree from like the outside. I kind of talked about like a skyscraper. We're kind of climbing down the tree, finding the right place to put it, creating the node, and then sticking it in there. So that's what we did last time. And that's fine. As opposed to letting the nodes of the tree find a home for this guy. So if we have a root node, we're just going to ask that guy to go ahead and place this wherever it's going to end up being able to find his home. Which solution do we like better?
Once I understood the second one, I liked the second one, but I had to get to that point first.
Well, that's good. I wouldn't have given it his homework if it was just busy work, right? Anybody else like the second one first? Or second one best? Other than the fact that you had to do it for homework. It's like, I really like the one you just wrote in class last time. It was like, I was better. I probably like the second one better as well. If we think about this from an object-oriented perspective, we want to encapsulate as much of our details as we can inside of other objects, so we don't have to deal with it. So up here at the binary tree level, we'd like to have our add look as simple as possible. This guy here is kind of hard to follow, right? It's like when you go by a building that's having a bunch of construction done on it, you have all that scaffolding on the outside. It looks very disorganized. You have no idea what they're really doing, right? They might just be replacing a couple of window panes or something like that. Okay, we don't really have an idea. But if stuff is going on inside, and they're having some stuff outside of one of the elevators on one of the floors, you're pretty sure something's happening right there on the building, right? So that's kind of the secondary approach where we're going to say, look, if I can add it here at the top level, here where we're putting an antenna at the top of the building. We're not going to have scaffolding. We just went up there and we're installing an antenna. Otherwise, we're going to go inside the building and we're going to go ahead and find out where we need to install this new thing. Okay? So that's where we dive into the nodes, and now we're able to use the nature of the binary tree for nodes to pass this value through their through their webbing until it finds its home. And this logic right here, we would say, is not very difficult logic, right? I mean, I kind of stretched this out. We could have shrunk this down a little bit using some ands or something. If it should go to my left, can I just place it to my left? Because do I have an opening? Otherwise, ask my left guy to place it. If it should go to my right, can I just put it on my right if I don't know if I have an opening? Otherwise, I'll ask the right guy to place it. No loops. The loop is built in to our pseudo recursive call. Now, why am I calling this a pseudo recursive call rather than a true recursive call? What is the recursive call? When I say recursion, what does that mean? Okay, when a function is implemented in terms of itself, or when a function calls itself, is the quick way of saying that. Okay, in this case, it might look like the add payload function is calling itself, but what is it actually doing? Yeah, it's calling one of its children. It's calling the same function that belongs to one of its children. Right? So it's not actually his own version of add payload, it's one of his children's version of add payload. We still will have the negative side effects of recursion. What's bad about recursion? Or what's a negative side effect of recursion? Slow, I would say no. It's not slow unless you use up all your system's memory and slow down the whole computer. It's probably similar speed to a loop, but it's certainly memory inefficient. So when I tell my left child to go ahead and add this guy, I'm putting this particular version of add payload, the one I'm currently in, on hold. because I can't finish. This call to add payload can't finish until my left child has finished his job, because this line blocks. I'm waiting for my left child to finish adding this payload. And my left child might have to delegate that task off to one of his children, who then might have to delegate that task off to one of his children. And as your tree gets bigger and bigger and bigger, this is going to become more and more of a problem. So there actually is an argument for very large trees that this approach out here, where's my binary tree, is better. Certainly it's more memory efficient right off the bat. It's just a little bit harder to follow because we're kind of doing the whole scaffolding thing. We're on the outside of the tree finding our correct home. Okay, but on a very, very, very large tree, that might make a lot of sense. Because otherwise you might have 30 or 40 internal, and I'm just making up a number there, it could be 500 internal calls depending on how big the tree is, right? Where you finally can plinko the value down to where it ultimately needs to go. All right, so then you can have trees that become pretty inefficient, especially if you get very lopsided trees. So somewhere in your book, they're going to be talking about tree balancing. Let me just look at the order in which they present this stuff in the book. Class is this, 300. Yeah, they go down. Well, they are going to talk about it here at the AVL trees. You're going to love these. These are after break stuff. Let's see if they talk about balancing inside of binary search trees. Yeah, see, if you look at the tree examples they're giving here, these guys are, they're very symmetric, right? So your most efficient tree is going to be a symmetric tree where everything is kind of, at a level playing field or close to level on both sides. Now, the way to get, based on what we know now, how do we get a tree that looks like this? Or the shape of our tree is at the mercy of what? Yeah, the order in which we add stuff, right? You could have the exact same values inside of a tree, but have very different trees, depending on the order in which you added those things to the tree, correct? So you can create a tree that is, like super, super heavy on the left side. You might have it might be a depth of 30 on the left side, and then the right side might have 2 nodes on it. Yet it has the exact same values in it as a very balanced tree might have, just because the order in which those values were added to the tree. Kind of makes sense? And we can't always control the order. All right. So one of the things we're going to look at is that it's a good idea, especially if you're searching a tree often, to keep that tree relatively balanced. All right, so that's where we are going to talk about AVL trees, which are a self-balancing type of tree, where after each insert, it says, how far out of whack am I? And then, is it worth fixing it? If I'm two levels too heavy on one side, then I'm going to rotate the tree. I'm going to do an algorithm that's going to bring that tree back into relative balance, which means the left and the right side are within 1 level of each other. So you have this effort of trying to keep the tree relatively balanced, but that's a lot of work to rebalance a tree. So you'd only want to do that if you're going to be searching the tree often. But that's the premise here. So this guy's talking about binary search trees. So here, this would be a unbalanced tree, right? So as they have you go through these exercises, you're going to see that if you luck out, and the thing you're looking for is over here on the left, it'll be fast. Otherwise, if it's over here on the right, it might be slower depending on how far down the tree you need to go. If you balance this tree, your best case might actually be worse. So in this case, our best case is going to be our average best case is going to be going down the short side, going down the short side here and finding our answer pretty quickly. Where the worst case is going down the long side, which might take significantly longer to find our answer. If we have a balanced tree, the average case will be better. But the quickest case might actually be worse, because now we've probably made this left side actually longer to balance out with the right-hand side. It kind of makes sense? So having a balanced tree isn't always better for each individual search. Having a balanced tree, regardless of how we get that balanced tree, but having a balanced tree has an average search time that will be better. If you look up here, one of the things they talked about is here's the, let's see. Yeah, so search time, they're talking about big O notation for searching a binary tree. So you can read through that, but this is talking about best case search time for how fast it runs. And that's going to become more and more and more of an issue as you get into larger trees. A small tree doesn't really matter. It can be completely unbalanced and it's going to feel like it happens instantaneously. Okay, so what I want to do next, so now they're starting to talk about ordering. I assume they're going to do breadth first, depth first, and let's just see what they... Well, they really don't. That's okay. Let me see if I see it at the high level here. Oh yeah, here's in order traversal. So we have in order, depth first, breadth first. Okay, so let's talk about these guys. So traversing a tree. So assuming we have a tree, whether it's balanced or not, we're not talking about balancing trees at this point. Just the tree is whatever the tree is. If we want to traverse a tree, we have some options. We can do an in-order traversal. We can do a pre-order traversal, or we can do a post-order traversal. Okay, and this has to do with when do we visit a particular node? When do we print out the values of a particular node? So if we look at our tree here, and let's look at what in order would be. So we're going to start at the top. In order says you visit the node you're currently at first, then you visit the left child, then you visit the right child. All right, that's what in order says. So an in order traversal of this particular tree would say we're going to visit 2, then we're going to go to his left child. We visit 2 again, because we're at his left child. Then we go to his left child. We visit 2 again. Then we go to his left child. We visit 1. Then we bounce up. We try to go to his right child. There is none. We bounce up. We go to his right child, and this is not his right child. His right child is non-existent, so there is none. We bounce up. Now we go to this guy's right child. And then we go to his left child. Try to go to his left child, there is none. Try to go to his right child, there is none. Bounce up, try to go to his right child, there is none. Bounce back up, we're done. Okay, so in order says visit a node first, then visit his left child. And then we have to do that whole algorithm again. Visit this node first, then visit the left child. Visit this node first, then visit the left child. Then visit the right child, then visit the right child, then visit the right child, so on and so forth. Make sense? So in order, if we were to print this guy out, just visiting it in order, we don't necessarily see a pattern here. Correct? So this is the order in which we visited those nodes. 2, 2, 2, 1, 4, 4. Now, let's look at Actually, I lied to you. This is not in order. This is pre-order. Pre-order says we visit the node first, then we go to the children. In order says we visit the left, then ourselves, then our right. Okay, so in order for this guy is we're going to visit the left, we're going to visit the left, we're going to visit the left. So we have that. Then we'll visit ourselves. There's the 2. Then we try to visit the right, visit ourselves. There's the 2. Try to visit the right, visit ourselves. There's the 2. Then we visit the right, but we're not at the 4 yet. So when we get here, we visit our left, which is that 4. Try to visit the left, not there. Visit ourselves. Try to visit the right, bounce back up, visit ourselves. Try to visit the right, there is nothing, bounce back up, bounce back up. So that's in order. So notice that in order gives us a sorted tree. 1, 2, 2, 2, 4, 4. So it's in order. All right, then we have post order. Where we visit ourselves last. So the root of the subtree is visited last. So post order says, okay, we can come in here, go left, go left, go left. So we visit the 1. Oop. Then we bounce up, try to visit the right. Then we visit ourselves. Oh. There's the 2. Bounce back up, try to visit the right, but then we visit ourselves. So we're visiting ourselves after post. Bounce back up, go to the right, go to the left, go to the left, there is nothing, go to the right, there is nothing, visit ourselves. Go to the right, go to the left, there is nothing on the right, so we bounce back up, we visit ourselves. I missed a, oh, no, we're fine. Then we bounce back up and finally visit ourselves. So that's the order for post order. So the very first thing we visited was the very last thing in here. But the very last thing we visited was the top of the tree. And we finally visited ourselves. All right, so these are various approaches to how we can walk through our tree. Make sense? And one is not necessarily better than another. It's going to depend on what you're trying to do with your tree. But let's go ahead and let's write some code that'll give us the correct, we'll visit the nodes in the correct order to traverse our tree. So we're going to go in here, we'll go into our binary tree, and we'll write a function, public void, call this traverse in order. And then we're going to have a traverse pre-order and a traverse post order. All right, so let's deal with in order first. How would you go about doing this? I'm going to encourage you to think similar to the homework assignment and move inside of the tree. We could certainly do the external scaffolding thing here. I think you'd find it to be a little bit difficult. We're actually writing this internally is going to be almost trivial. Go ahead.
So you have to keep finding the leftmost node or whatever they're called.
if I'm this guy, so we're looking at it internally from a node perspective. So if I'm that guy and I've been asked to visit in order, what's the first thing I do? Okay, ask if I have a left child. I do. So what do? I tell him to visit himself in order. So now I'm the left child. I'm asked to visit myself in order. What do? Ask if I have a left child. I do. So I'm going to pass the buck on to him. I'm supposed to visit in order. Do I have a left child? I do. Then he looks down and says, do I have a left child? No. So I'm supposed to visit myself next in order. So I'll print out a 1. Then I'm supposed to try to visit my right child. Do I have a right child? I do not. So I'm done. My version of this ends. This guy pops back up. He just visited his left child. So what's the next thing that he does? Himself first. In order is left, then yourself, then right. That's the in order. So we'll visit our self. Then we'll check if I have a right child. If I do, tell him to visit in order. Otherwise, in this case, he doesn't, so he's done. Bounces back up. This guy will visit himself. Then he'll ask, do I have a right child? He doesn't, so he's done. Bounce back up. This guy visits himself. Then he asks, do I have a right child? If he does, he tells his right child to visit in order. First thing the right child says is, do I have a left child? I do. So he says, visit yourself in order. Left child says, do I have a left child? I don't. So I'll go ahead and print myself. Then I say, do I have a right child? I don't. So I'm done. Bounce back up. This guy then prints himself. Says, do I have a right child? He doesn't, so he's done. Bounce back up. We're done. When we walk through it like that, it sounds complex, right? It sounds like a difficult thing to write when we're saying it out loud like that. But if we actually go into our nodes, and let's think about this from a nodes perspective. I'm going to create public void visit in order. And visit in order says visit my left node, then myself, then my right node. So if this dot left child is not equal to null, then this dot left child dot visit in order. So we'll try to visit our left child. Then we're going to print ourselves out. System.out.print this dot payload. Then if this dot right child is not equal to null, this dot right child dot visit in order. That's visit in order. If I have a left child, ask him to visit himself in order. Then, whenever he's done, however long that takes, then I'll go ahead and visit myself. Then I'll ask my right child, if I have one, to visit himself in order. Come back into our binary tree here. Here's our traverse in order. If this dot root is not equal to null, if I have a root node, then I'll go ahead and I'll say this dot root dot visit in order. And then I'll kick it down a line because those guys were all prints. So that print lin will knock it down a line. So that'll be traverse in order. Go back to main activity. bt.traverse in order. We've decided this guy should have an output of 122244. I probably should have put some spaces in there, but 1222244. All right, so I'll put our spaces in there so it's a little bit easier to read. All right, so that's visit in order. So all that logic was moved in here. You see how starting to think recursively can actually be pretty beneficial? Because if you look at it like this, like, that's not a lot of logic, right? But because we're doing that along each node along the way, there's quite a bit of logic that's actually happening. But that looks pretty easy.
This only works because we have specified that we're going to organize the node in a specific way. If it was just
Oh, correct. Yeah. Well, actually, that's not true.
do I have a right? Do I have a left? No. Okay.
That's actually, I mean, not that we would have organized it in a specific way. This visit in order thing would work on any binary tree.
Right.
But we've applied the binary search tree rules to it, which say things to my left are less than or equal to me, things to my right are greater than me. But this visit in order thing would work on any tree that has at most 2 children. It might not mean much, but it would work. In this case, it might be more meaningful because the children do have an order to them. Okay, so now I'll write public void visit pre-order. Paste that code in there. Oh, I'll steal the contents instead. All right, so how would I modify this to visit pre-order? Okay, which means I have to do what? Move this line to there. Done. Now that visits pre-order. I visit myself first, then my left child, then my right child. Visit post order. What do I change here? Take this line, move it there. Let's visit post order. Let's go back to our binary tree. Steal that code. Here's our pre-order. Here's our post order. We'll visit the root node pre-order. We'll visit the root node post order. bt.traverse pre-order. bt.traverse post order. So there's our 3 traversals. Go ahead and run this guy. Here's our guys there. So let's see, the first one was in order, so that's the 1222244. Then we did pre-order. So pre-order, did I write pre-order? Did I do pre-order wrong? I know we screwed up here with the first time. Pre-order says visit this guy first. So we visit ourselves, then we visit our left. So visit ourselves, then we visit our left, visit ourselves, then visit our left, visit ourselves, try to visit the left, try to visit the right, try to visit the right, try to visit the right, come back up, visit the right. So we have I did do this wrong. In fact, where's the one from? Oh, no, we did. We visited this guy. Now we visited the 4, and we visit his left, which is the 4. try to visit left, try to visit the right, bounce back up, try to visit the right. So that's pre-order. 22144. What happened? I built the same tree, didn't I? Oh, hold on. I bet you we have some copying and pasting issues here. It's always the copying and pasting issues. Yep. So if you're visiting in order, we should always visit in order in here. If you're visiting pre-order, we need to visit pre-order in here. If you're visiting post-order, you need to visit post-order. You can't fake it the very first time and then just keep visiting in order after that. Yeah, so if you're in visit post-order, keep visiting post-order. This should look better now. All right, so there is our 222144. So that's our pre-order. Then we have our 122244, so that's in order. And then post-order is 122442. That's our post-order. All right, so that is us looking for values in different ways. Now, if you're just doing a plain search, you're looking for a value, which of these do you think is probably the one that's going to be most efficient? In order. Why even have our tree sorted unless there's a reason to have it sorted? Because that allows us to pinpoint into this. Now, there's a type of search I don't actually think we have done before. Have we written a binary search before? Did we do that in 200? Okay. So just review that real quick. So binary search, this has nothing to do, well, it has very little to do with binary trees except for where their name was derived from. So binary search requires that the list of elements is in order. So it requires that it's sorted. All right, so we have to have data that's sorted first. So we might have 1, 1, 2, 3, 4, 6, 9, something like that. All right, so we have some sorted data. To do a binary search on this guy, it's also called a dictionary search. All right, so the very first thing we do is we open up the dictionary somewhere. Let's say we're searching for a word. We open up the dictionary to roughly the middle, and we point at the very middle word and say, is this the word we're looking for? If it is, we're done. We found it. If it's not, we ask, should the word I'm looking for come before this word or after this word? If it should come before the word, we rip the dictionary in half, dealing only with the left-hand side because it should come before. We turn to the middle of that guy, point. Is this the word I'm looking for? So we keep cutting our data in half until we finally land on the right answer. Does that sound like something we've written? Okay. So if we're looking for a 1 in this case, we have to decide which of the halves we would look at. So I'm going to go to the very middle. We'll look for the value that's in the middle. So let's say we're looking at the 3. Should a 1 come before or after that? Should come before that. So we forget all of that, and now we're only dealing with this. Go to the middle of that, we find our 1. So it allows us to dig into our data much quicker rather than having to linearly go through our data. Now, in this case, so who are competitors to this? Well, a linear search would be a competitor, right? A linear search would start at the beginning of a list and walk towards the end looking for the value as it went. Now, in this particular example, a linear search actually would have been faster because we were looking for a 1 and we would have found it right away. Again, presuming that a linear search was given sorted data. So linear searches do not require data to be sorted, because we're effectively just going through our pile of data looking for our answer. Is this it? No. Is this it? No. Is this it? No. The relationship to each individual data point doesn't mean anything. All right. So we would say this kind of goes back to what we mentioned a few minutes ago about average search times. You're going to have situations where an individual search on an algorithm that isn't necessarily known to be all that fast actually is really fast just by sheer luck. But when we look at some of these different searching algorithms, what we're really focusing on is what is the average search time, all right, for these different things. So the average search time for a binary search will be faster than the average search time for a linear search. Go ahead.
What is the time complexity of each of those?
Binary search is n squared. No, I'm lying. Linear search is n squared. Binary search is n log n, I believe. Let me... I think they have searching sorting algorithms here at the beginning. So let's just look at searching algorithms here. All right. Quicker thing. Big O searching algorithms. Complexity, cheap cheap. All right, where's our linear? Oh, those are sorts. I want searches. I just want the quick little list. Big O cheat sheet. It shouldn't be, because really when you think about time complexity, you are, I think the easiest way to think about it is the number of comparisons, the average number of comparisons. So there shouldn't be a reason why we can't find search things. I mean, they're showing us searches here, but they're not telling us what kind of search they're using. Part of that is because we don't have a lot of searches to choose from. I'm pretty sure what I told you is accurate. That linear search is n squared, and binary search is n log n. We call it 77%. Says for which?
Is it n squared or 2 to the n?
For linear, I think it's n squared is the average search time for a linear.
Oh yeah, that makes sense. Because at most you have to go through it 10 times.
Yeah, what you said is worst case.
Right.
2 to the n would be worst case. And best case would be 1. Found it very first time. Okay, so let me go back to where we were here. Let's see if they give us a cheat sheet for O notation. Now, speaking of which, so this O notation thing is giving us kind of at a glance what performance can we expect from a particular algorithm. So really any algorithm can have an O notation. but we kind of have known algorithms. When we're talking about searching or sorting, we have kind of known things that give us the value for it. And we're going to say this is going to be the average search time or the average sort time, that type of thing. Because depending on the current order of the values, you might have to move things different amounts. So, you're not going to necessarily hit the exact, but you're looking for what it is roughly. Let's see if they give us. Yeah, so here's some of like the options, and they're looking at it from growth rates for related to time. So it looks like they're giving you some number of seconds as a starting point, just to see how long something takes. So big O for linear search. That actually makes sense. Is order n, because n squared would be worst case. No. N is worst case. So this is doing it on worst case. Oh, it's runtime complexities. So worst case for linear search is n. You're going to have to look through every single one of them. We've done merge sort. Let's see. Did they give us a binary search? Binary search is log n. Would be your. Well, I still think. That makes sense. But this is runtime complexity, not necessarily average search time. So this is based on the time it would take to run. So they're saying binary searches, order log n, which is less than n, so that's faster than linear search, which is order n, which is slower than binary search, but faster than both of them. Well, actually, no. Merge sort is n log n, which would be in between those two guys. That's actually an interesting thing to discuss here. So we learned merge sort, right? We wrote merge sort. And merge sort kind of felt harder than binary search or any of those things, right? But we're looking at, even though they were comparing searches and sorts here, we would have said that merge sort was difficult, but we were getting something for that difficultness. That doing the merge sort approach, it was harder, but maybe it was also going to be a lot faster. Where this actually says, well, it's going to be better than like a linear search, but in here, we're still not as good as we could be. How can merge sort get a lot faster in computing today? Where this kind of gets thrown out the window. Think about the nature of merge sort. How did merge sort work? Yeah. So when we did merge sort, let's just look at that as a quick example. All right, so merge sort, we're just going to pick some random values that I have random values here. Those were in order, so I need to give myself new random values. Let's just start with that. All right, so merge sort says, is this sorted? And as you point out, it's not trivially sorted, so it's not the one list. So we divide it in half, and we try to sort the left half. 3, 1, 2. Is that trivially sorted? No. So we divide it in half, then we try to sort the left half. Is that trivially sorted? No. We divide it in half, then try to sort the left half. Is that sorted? Yes. Then we try to sort the right half. Is that sorted? Yes. Then we merge these guys back together, giving us a 1 and a 3. which since we're changing that in memory, that's going to update throughout. All right, so then we get to the right half of this, which is a 2. Is that trivially sorted? It is. So we bounce back up. We merge these guys together, which is going to give us a 1, 2, 3. Then we bounce back up. We deal with the right half, 849. Is that trivially sorted? Nope. Did I have my, which was my bigger, the left or the right? Left was bigger, okay. So I look at 84, is that trivially sorted? Nope. Split that in half. I look at 8, is that trivially sorted? Yes. I look at 4, is that trivially sorted? Yes. Then I merge those. That's 4, then 8. That changes everywhere else. 4, 8. 4, 8. Then I do the 9. Is that trivially sorted? Yes. I merge these guys together. I just happen to already be in the right order. 4, 8, 9. So I'm done here. Then I merge these guys together. So which should come first, a 1 or a 4? A 1. Which should come first, a 2 or a 4? A 2. Which should come first, a 3 or a 4? A 3. Then the other ones all just win. So there's my sorted values. All right, so that's how merge sort works. Everybody remember that now? How, with modern computing, can we make that a lot faster? Keeping the algorithm identical. So we just saw, based on complexity, it's not necessarily that fast. It's faster than like a really crappy case, but it's not that fast. Because we're doing all the work on a single computer. Is this a problem that could be divided up? So an example you maybe have heard me say before, when we talk about machines, just computers in general, when you start getting into a computer that has, 2 cores or 4 cores or dual quad cores or dual 6 cores, or, you have all these extra cores in the machine, is more cores better than less cores? Well, the answer is it depends, right? If you are doing one task, and only one task, you would rather have one really fast core than 2 cores that are almost as fast. The example that that I've used before is like if we're changing a light bulb. This goes back to the joke of changing a light bulb. If I can change a light bulb at speed 10, and the 5 of you can change a light bulb at speed 9. Okay, but there's 5 of you, and there's 1 of me. Who's going to change a light bulb faster? I am, because changing a light bulb is a one-person job. All right, so that single core that's a little bit faster is going to be better for that job. Now, let's assume that we are raking leaves on campus. And I can rake leaves at speed 10. Each of you can rake leaves at speed, you can go even less than 9, but let's just use 9 as the example. Okay, who's going to rake all the leaves on campus more quickly? The group of 5 people. Because even though each of you as individuals might be a little bit slower than me, you're going to be able to cover a lot more ground because you can divide up campus into 5 pieces, right? And do the work. So when somebody has this computer that is, has all these cores in it, the example I've used in the past is like with Macs. You can get a Mac Pro that has dual 6 cores in it. So you have 12 cores. There's actually 24 logical cores because each one has hyper-threading. Okay? Or you can get like a MacBook Air that has a low-powered dual-core processor. Now, or some of the newer ones have quad cores, I guess. But now when you're checking your email or you're browsing the web, those 2 machines are actually going to feel pretty similar in speed. So what's a modern computing task that is very divisible, labor divisible? Something that you might use your computers for that would really be able to take advantage of multiple cores. Actually, gaming would probably not be a great example. Gaming would do pretty well with a couple of cores. But with gaming, you really want to have the fastest cores possible, which you usually can accomplish with less cores. So gaming would probably, a dual core or a quad core would probably be better than a single core as long as the clock speeds were similar. But gaming is not going to benefit from like massive numbers of cores. Things like video conversion, animation rendering, things like that. These are very division of labor problems where, so a good example would be if you're converting a 1 hour movie, let's say, to MP4 from whatever, let's say it's an AVI now and you want to convert it to an MP4. If you're doing it in that MacBook Air, that basically feels just as fast as that super expensive Mac Pro for normal tasks. That MacBook Air is probably going to take an hour and a half to convert that video. If you do that same thing on the Mac Pro, how long would you guess it's going to take? Matter of minutes. Maybe it takes 3 minutes, something like that. Because you have so many cores to work with, and regardless of how fast those cores are, if you can divide up that video into 24 pieces and convert 1/24 of the video on a per core basis, you're going to speed it up by quite a bit. Maybe not 24 times faster. I mean, the reason I said it's going to be a matter of minutes is because the cores on the Mac Pro individuals are faster than the cores on the MacBook Air, so they win both ways. There's more cores and they're faster cores. But maybe you don't quite get 24 times the speed. Why wouldn't you get 24 times the speed? If you have 24 times the cores, why wouldn't you get 24 times the speed? Why might you get like 22 times the speed? If you have one person doing a job versus 10 people doing a job, and let's say they all can perform the work at the same pace. Are the 10 people going to do it 10 times faster, or is it maybe going to be more like 9 times faster? Yeah, there's overhead related into the organization of it. Who's going to do what? When are you done? Don't do the same work twice. That kind of stuff. So there is overhead involved, and also when you talk about from an operating systems perspective, we had that class 350 operating systems. In an operating systems perspective, when you think about more modern operating systems versus older operating systems didn't have to worry about multitasking. They could just do one thing at a time, no big deal. So they were much simpler to write. So typically with great power comes great responsibility type thing. So if you're going to have an operating system that can do a lot more stuff, it's also going to be much more difficult to write. The complexity of it goes up. And if you're thinking about how do I generically manage a whole bunch of cores working on the same problem in parallel, that maybe becomes a difficult task. So you have quite a bit of overhead there. So, maybe you're going to get 22 times the performance or something like that instead of 24 times the performance, but you're still getting a lot more performance. So, the juice was probably worth the squeeze, as they might say. So, merge sort would do better on a multi-core machine, right? Especially if you had an infrastructure in place where you could actually dictate this core deals with the left half, this core deals with the right half, this core deals with the left half of the left half, and so on and so forth. If you can really break it up into those individual pieces, then you're going to get a lot more speed out of it, won't you? Because at that point you have effectively, a little list like this, you can, you'll break each part down to one core doing one little piece of the work. And most of the work is actually going to be communication. So it'd be a lot quicker at that point. Now, more modernly, and this isn't necessarily something that we have exactly today, but we're moving pretty quick towards this, is this idea of a distributed operating system, where you have parts of your operating system split across multiple computers. So instead of multiple processors within one computer, you can now have 20 computers working on this problem, where maybe you have one central computer that is dividing up all the work and saying, okay, you work on this part of it, you work on this part of it, you work on this part of it, so on and so forth. And then ultimately they all do their work and then bring it back together. And that center guy kind of puts the puzzle back together. That's his job. So now you're not limited by how many cores fit into a single computer. You're limited to how many computers can you have together in a network. And if each one of those computers also then has multiple cores, they can do 4 times the work, let's say, if they have a quad core. You can create quite a bit of computational power across the internet, correct? And that's effectively what we're doing today when we're, I think I've shown you that website, the distributed.net website before for like cracking. Have I showed that to you before? The site's very old. So distribute.net even looks old. So this is old school website, but it's still running today. So the point of this, so this deals with distributed computing, and the point of this site is for stress testing encryption algorithms. So you take usually encryption algorithms when you have some number of bits. So how many of you have had the security class with Dr. Wall? Nobody's taken the security? Oh, you're in it now. So when you talk about, have you talked about encryption yet and how many bits a key might be, public-private key? Okay. So when you talk about public-private key encryption, you're guessing what the key is, the kind of like the password to unlock something. Well, if you have a 4-bit key, that's not very secure, right? You're going to test every permutation of a 4-bit key is not going to take you very long. If you have a gigabit key, 1,024 bits, that's 2 to the 1,024th unique keys. That's a big number, right? So we'll just use that as an example. So let's say we have a gigabit key. So we have 1,024 bits. Actually, that would be a kilobit key. A megabit key would be 1,000. We'll just do the kilobit key. That's fine. So 1,024-bit key. That means there's 2 to the 1,024th possible keys to try. You wouldn't think about this in real life. You're trying each key in the lock, okay? And we can only try them so quickly. Now, if we each have a copy of the lock so we can try 2 keys at the same time, are the 6 of us going to be able to test those keys more quickly than one of us? Sure. Could 600 of us test it even faster? Yeah, so the idea of distributed.net is it's an approach against a lot of these encryption algorithms. When we didn't have the internet and we didn't have the computational capacity that we have today, the security of an algorithm could be based on the number of permutations of the key, because it would take longer than a lifetime for somebody to, on average, to figure out the correct key. And sometimes the security is based on, how long is the information good for? So let's say you have a top secret memo that comes out of the government or something like that, and that data is only good for a week. Well, as long as it takes longer than a week to for the fastest machine or whatever to decrypt it, you're fine, because maybe it's public knowledge in a week or something like that. All right, so when we look at the security of these encryption algorithms, we might look at how long would it take to crack. Well, now if we could have a whole bunch of computers working on the problem simultaneously, it becomes a lot more interesting. And the funny story with distributed.net, this is something I did, was messing with. I mean, this is 18 years ago, something like that, 20 years ago. And I know we're out of time. Let me just tell this quick story real quick. So the government had this new encryption algorithm called triple DES, DES. And what they did is they said this was uncrackable. I forgot the exact details of triple DES. I think it was like 256-bit keys or something like that. Uncrackable. And they wanted it to be stress tested by distributed.net. Government promised this thing is unbreakable. They figured that distribute.net would just work on this. It got cracked in like 17 seconds. Like no time whatsoever. Because you had so many things working on the problem at once. And that's the world we live in today. So most of our modern encryption algorithms are not just based on the security of number of bits. They have other things like a lot of them deal with prime numbers and things like that now. But in any case, something like merge sort, and this is where kind of that time complexity stuff becomes maybe less important today because we can distribute things so much. Merge sort can become very, very, very fast if we distribute it across a lot of stuff. All right, so what should I give you homework over break? All right, no homework over break. If you're traveling, have a safe trip. I will see everybody a week from next Tuesday.